Okay, some of the wise words what we said here. We're doing M2. We're going to be doing some elasticity here, and we're going to be using hard questions at Hooke's law. We're going to have Dhiraj on the show, and he's going to show us.
Hello, Sam. Pleasure to meet you. Pleasure to meet you.
It's going to be amazing.
Okay. We have a question here. A ball is hung from a string of mass 4 kilograms. We have a natural length of 2 meters and a modulus of elasticity of 29.4 newtons. Now we're going to be trying to find out the spring extension. Right, so tension is equal to the modulus of elasticity times the extension divided by the natural length. Now we're going to be trying to find out the extension here. So we're going to rearrange the equation so we get L times length times tension divided by lambda is equal to x. So extension is equal to tension times the original length divided by the modulus of elasticity. So if we input the numbers, we should get extension as 2 2/3 meters. The mass, which is 4 kilograms, the force acting downwards is going to be 4 times gravity. Gravity, which is 9.8, so it's 4g. And because the ball is in equilibrium, the force acting downwards is also going to be the same as the force acting upwards.
Quite a hard question here. The question is, find the coefficient of friction of this ramp here that the ball has gone down. The ball is attached to a string at the top and it's going to go down 2 meters. At the 1 meter mark, it will have reached its natural length spring of 1 meter. Its modulus of elasticity is 40 newtons, and the angle here is tan. It's just theta. And so we just want to find mu. We can write out some equations here. Our first equation we're going to write out is that the elastic energy equation, where E is equal to lambda x squared over 2L. That's the equation for elastic potential energy. We know that the gravitational potential energy lost, because it's going to be fully converted into elastic potential, is actually going to be equal to the EPE, but some energy is going to be lost to friction, so it's also going to be frictional energy. This is not very well calibrated. Frictional energy. Okay, so we're going to start off with working out GPE here. In order to do that, we need to know the height, this point here. We can do tan minus 1, 3 over 4. And we'll get the angle here, which is actually, I believe, 36.9. Once you've got 36.9, we can do SOHCAHTOA trigonometry using the hypotenuse, this angle, to find the opposite. So that will be hypotenuse times by sine 36.9. And that will get us the height to be 1.2 meters. Once you've got that, we can substitute that into energy equals delta HMG. Change in height is 1.2. Mass is going to be 2 kilograms, and G is going to be 9.8. And I believe if we plug those numbers into our calculator, we get that the total energy lost in gravitational potential is 23.52 joules of energy. That's this part here. We're a third of the way there now. Now we want to work out the total elastic potential energy gained here. And that's going to be quite a hard one here. We know that we don't know E. We do know X because it's the spring extension. It'd be 1 squared. We know lambda, and we know 2 times length. So we know that 40 lambda times by x squared, which is 1 squared, divided by 2 meters equals 20 joules of energy is our elastic potential energy. So now we have an equation form. We've got 23 equals 20 plus this frictional energy. We don't know what it is. Now to work out the frictional energy, we need to use another equation here. F equals mu R. We don't know F, but we can work out R here, and then we can put it in terms of mu. So R, if we make some room on the board here, actually, to do this, quite a big one. If you look at this in detail, we can see that the ball is on a ramp here, and that is being pulled down by 2G. And this is the normal here, and this is where it's going down. So this is going to be the frictional force here because it's pulling it back up. We know this angle here, it was 36.9, and therefore we know this angle here, which is also going to be 36.9. So we can find out the component that's pulling it downwards into the ramp, which is actually going to be 2G cos 36.9, and therefore, because it's in equilibrium, because it's not moving upwards or downwards, the reaction force also has to be 2G cos 36.9. And once we have that, we can do 2G cos 36.9, it's hard to read, and because force times distance equals energy, we know that this force times the distance travelled 2 equals the energy lost to friction. But we don't know, it has to be F equals mu R, and so we're going to put it in terms of mu here. And so the total energy lost to friction is 31.36 mUs. We don't know what mu is, and that's what we're trying to find out. Okay, now we're getting an equation here, a big one which you can start to solve. Gravitational potential energy is going to be 23.56 equals 20 joules of elastic potential plus the energy loss to friction, 31.36 mUs. So we can then take away 20 from both sides, 23.56 minus 20, divide both sides by 31.36, and we'll be left with one letter, U, which would actually be 0.112. That's the coefficient of friction of the plane.